Okay, good morning, everyone. I'd like to first thank the organizer, Arka in particular, and all the others for organizing this great conference. It's a real pleasure to see everyone again and to be back in person, which is great. So I'll be talking about cosmological weak lensing. I'll follow up on Bhuvnesh's nice introduction on the subject, and I'll be focusing on a different and complementary approach to the analysis of weak lensing surveys, in particular map-based statistics and machine learning approaches, techniques that he briefly mentioned. Generally, our standard model of cosmology it has been confirmed through a combination of different cosmological probes. Here, I've listed them in sort of the main categories. So there's a cosmic microwave background giving information at early times. There's what we would call the geometrical probes, supernovae and gravitational waves, which gives information about the geometry of the universe and on the background expansion history. And then there's generally the clustering of visible matter, right? Could be galaxies, clusters of galaxies. And then there's this approach using gravitational lensing, which has a special place in cosmology because it allows us to directly probe the mass distribution of the universe, which is more easily predicted than the distribution of visible matter that involves very complicated baryonic and physics and astrophysics. I'll be focusing on this probe. As we'll see, the price we pay for this sort of cleaner physics is that the measurements are more difficult and noisier and quite challenging. But as you'll see, and as Bhuvnesh already described, this field has made a lot of progress in the last few decades. So let me, maybe for the sake of students who maybe are not too familiar with lensing, I'll show the principle of lensing with this nice, nice, I don't know, but a little cartoon. So you imagine being an observer on the left and a background galaxy on the right, and this is what it would look like if we could see its intrinsic shape. Then if there are no density inhomogeneities along the line of sight from the galaxy to the observer, then the observer will simply see the intrinsic shape of the galaxy. However, if there are density perturbations, which is basically clusters of galaxies, or any density perturbation generated by cosmological structure formation, then as a consequence of Einstein's theory of general relativity, the photons from the galaxy to the observer, instead of traveling in a straight line, will have a perturbed trajectory. And this will have a number of effects, but the one I'll be focusing on is that instead of seeing the intrinsic shape of the galaxy, the observer will see a distorted shape of the galaxy. And in fact, one can show that the distortion, which can be described by a 2x2 matrix, which is the lowest order mapping between the intrinsic shape and the observed shape, lens shape, can be described by a 2x2 matrix, which is equal to the integral along line of sight of the derivative of the gravitational potential perpendicular to the line of sight. So that gives us basically a direct measurement of the projected gravitational potential derivatives. Or another way you can also phrase that into a projection of the density field along the line of sight, and the weight is given by the redshift distribution of the background galaxy that we use. And also there's a geometrical kernel which peaks roughly halfway between the observer and the galaxy that we use. Now to illustrate this effect, let's look at another cartoon. So let's suppose we have now we're looking into the plane of the sky. Let's suppose we have some galaxies which all have the same shape and same size and so on, for, of course, highly simplified situation. Let's suppose they would look like this in the absence of lensing. And now let's suppose that between us and these galaxies, there's some density perturbations. So the bright region would be in white, would be over densities, and the dark region would be under densities. Then instead of seeing these galaxies, the intrinsic shape of these galaxies, they would appear distorted. Here, the effect has been greatly amplified, so we can see it by eye. As I'll say later, the effect's actually quite small. But you can see that the galaxy shapes are distorted. I can go between the two. Right? Oh, sorry. A little bit too fast. And one can actually map the distortion and quantify it by what we call the shear, which is an hourless vector field that one can, that is a function of position on the sky. And for example, you see that generically we get tangential distortion about overdensity. You see it quite well at the corner here, where you see the distortion or the shear here, which is tangential about this overdensity here. Okay. Now, so what we can do is we can measure the average shape of galaxies in a region of the sky. That gives us a measurement of this distortion of the shear. And then from the shear, we can map it back to distribution of mass on the sky. So that gives us a distribution of mass. And because the matter density is dominated by dark matter, this effectively gives us a map of the distribution of dark matter in the universe without any assumption about the physical property of the dark matter. Yeah. Very good. Yeah, very good. So here in this cartoon, I had drawn the galaxies as circular, but in practice, of course, they are not. They have their own ellipticity. We call it intrinsic ellipticity of the galaxies or intrinsic shape. It turns out that, what lensing does is it induces a coherent alignment of the shape of galaxies. So the idea is that in the absence of lensing, the galaxies will be randomly oriented, and lensing creates a correlation in their shapes. And that's what we're looking for. Now, in practice, there's actually a little bit of alignment also of the intrinsic ellipticity or intrinsic shape of galaxies is called intrinsic alignment. That needs to be corrected for. I'll be briefly mentioning it later. However, we can do that by losing the fact that these two effects, the lensing and the intrinsic alignment correlation, have completely different redshift dependence. So we can separate one from the other to some degree. Yep. Yeah, we can. So what I'm focusing on here is what I call weak lensing. In fact, let me show you. Let me get to your question in 1 second. So let's look at a more realistic simulation. This is a simulation using ray tracing, so n-body simulation that shows a typical density and shear field in the universe in the box. This is a 25 arc-minute by 25 arc-minute simulated region. What you see again in light blue and dark blue are the density, the projected density. So these are over densities, and you see and these are under densities, and you see the shear. And what I'm focusing on is the weak lensing, where the effect is, which is the typical amplitude of the effect in random region of the sky, and that's typically gives distortion of about a few %, very small distortions. Now, if we go to the core of clusters of galaxies or of galaxies, then we have much stronger distortions. This is what we call strong lensing. In that case, you can even have, as you said, multiple images. You can have very strong arcs, distortions, and time delays, and a lot of other effects. However, these are a very interesting system, but they're very rare. And if we want to map the distribution of matter in the universe statistically, then we are using we are in the weak lensing regime, which is what I'm focusing on here. Very good. Now, this effect is quite weak, so it's been quite difficult to measure. One needs to correct for a lot of effects, in particular instrumental effects that can affect the measurement of the shapes of galaxies at the % level or less now. But there's been lots of progress, and now this is very well measured. Bhuvnesh showed results from the dark energy survey. Here is a picture of the telescope and the camera, which is at the focus of this 4-meter telescope in Chile. At the time, this was one of the most, well, still is one of the most powerful cameras, wide field cameras for astronomy in the world. And this survey will cover eventually 5,000 square degrees and 200 million galaxies, as Bhuvnesh said. And this is already a different data release that has been done and the analysis that has already been done. And Bhuvnesh already showed the results for the mass map. So this is a slightly different version of the mass map done with the year 3 release. So you see this, the mass overdensity, the mass projected mass overdensities in more brighter colors, and the dark colors are under densities in these about 4,000 square degrees with about 100 million galaxies. So once we have a map like this, or more precisely a shear catalog, so a set of point galaxies with a shear measurement, one can do various kind of statistics and compare to prediction from a theoretical model and constrain our cosmological model. So one approach, which has been widely used, is to use the two-point function. As I said, Bhuvnesh already showed that. So what we can do is we can measure the two-point correlation function of the shear by taking pairs of galaxies. We can do it tomographically by subdividing the galaxies into different redshift bins. So you see here that we have 4 different redshift bins. So this is a redshift, and in different colors, you see the redshift distribution of different subsample of galaxies, which are selected using colors. And then we can measure the autocorrelation and the cross-correlation of the galaxies in this bin. So along the diagonal here, you see the cross-correlation between bin 1 and bin 1, bin 2 and 2, 3 and 3, 4 and 4. And there's a cross-correlation between these bins. Because the shear is a RLS vector, there are turns out two correlation functions. So there's one correlation function here, one correlation function here. And we can then, to infer cosmology, what we can do is we can make predictions for these correlation functions in a given cosmological model and fit it to the data. So that would be the more classical approach, right? We measure a statistics from the data. We basically compress the information into a statistic. Then we have a theoretical code that can predict the statistics for a given cosmological model. We adjust the cosmological parameters using Bayesian inference to get constraint on the cosmological model. Okay, and when we do that, we get the results that we've already seen. So for example, if we look at the sigma 8 or S8 versus omega matter, the measurement from this DES-Y3 is the green one, which we can compare to the CMB with this 1 to 2 sigma tension. And we also compare to the kids, which is another survey, which is the blue results, which tends to give a slightly stronger tension. And this other survey, HSC, which is the red ones, which gives also somewhat more intermediate results. You see a summary of the tension here. This is this S8 parameter, the amplitude matter fluctuations. This is for this DES-Y3 measurement, the kids measurement. You can focus on the blue one and the HSC measurement, which you see here, and Planck on the right here.
Can I ask a question on this slide? So the HSC here, there's results from CL and psi plus minus. So like I remember thinking about Euclid many years ago. We were doing forecasts using CL, and then when doing DES analysis recently, it's with psi plus minus. So can you explain like the benefits and differences of using one versus the other, and why does DES choose psi plus minus rather than CL?
That's right. So in terms of the information, in principle, they're the same because they're the Fourier transform of each other. The CLs and the correlation function, one's in real space, one's in Fourier space. However, in practice, they're different. And in particular, the correlation function in real space is easier to measure because it's easier to take into account the mask of the survey. So if there's a complicated mask with lots of holes and everything, in the correlation function, you just select pairs of galaxies, and you just don't have galaxies falling into the holes by definition because that's part of the mask. That's the mask region. However, for the CL, one needs to correct that, and it's a bit more difficult. However, the advantage of the CL is that the measurement at different L, at least with the full sky, are independent. So each L measurement gives an independent measurement, while the correlation function, which is a function of angle, gives a measurement at different angles, which is correlated. So that's the price you pay. As the survey area increases, the CL becomes more and more feasible because the mass becomes larger and larger, easier. So people in the past could not do the CL measurement, and now we can, and typically we try both. Yep.
And so that's why Euclid might switch to CL because it's a wide.
Yeah. So I mean the larger. Yeah. So I think they will. I mean, I think CL will become the primary measurement, but they will also try both to see. I mean, in practice, what it does also, it gives slightly different weight to different scales. So it's worth trying both and making sure that it's consistent with one another, basically. Yeah.
Okay, thanks.
Okay. Good. One can also add clustering to this measurement. So this is an analysis with lensing plus clustering. You see the resulting effect on the S8 omega m plane. So in maybe we can see here in blue is lensing only. So we can look at S8. Blue is lensing only. The clustering plus cross correlation of clustering and lensing is the orange, and together it gives the gray. So we had stronger constraint by combining with clustering. We add more nuisance parameter, more information, and so we can get more information. And then the comparison with Planck is here. So this is the so-called 3 times 2 points, so lensing plus clustering and cross correlation compared to Planck. And in orange, the combination with Planck. And this does 3 times 2 point measurement. So again, small tension there as well. Okay, now can we go beyond the 2 point function and measure more than the Gaussian information in the map? The answer is yes, and that's very important. Buvnesh mentioned the 3 point function, but there are also other approaches. And the idea is that the weak lensing field, this is another simulation, is very clumpy, so it's very non-Gaussian. You see an example of a Gaussian field with completely different power spectra here from the cartoon before. Typically, a Gaussian field has less clumps than the weak lensing field. And the reason is because these clumps are nothing other than clusters and groups of galaxies, which are nonlinear structures that have collapsed through the nonlinear evolution of structure formation through gravitational instability. So that's where fundamentally, on small scales, we have non-Gaussian and nonlinear evolution that gives us non-Gaussian information. So how can we tap the signal? Well, we can use higher correlation function, 3.4 point. Another technique, which is now being worked on and a very fast development, is using what we call map level statistics. One example would be peak statistics. So basically what we do is we take the map. So this is the actual map data with the DS data. And we can detect the peaks. So we can, for example, take all the yellow region, detect them, and count them. And that, it turns out, is sensitive on the cosmological model because it probes the amplitude of fluctuation, it probes the tail of the distribution of the fluctuations, and has a complementary information to the 2 point function. So that's what we did. This is a study led by one of my students at ETH, Dominic Zürcher, who did analysis with the DES Y3. And what you see here is a measurement of the peak amplitude for different of these tomographic bins. So here, for example, let's pick the first bin. You see the amplitude. The number is basically counting number of peaks as a function of amplitude. So this kappa is the amplitude of the peak. And you see this amplitude here. The data points are the solid line. You can see it for bin 1, bin 2, bin 3, bin 4. One can also multiply the two maps and do actually cross correlation between the different redshift bins as well for peaks, which is quite powerful. And you see the measurement here. Now, the difficulty is so the advantage that we can measure non-Gaussian statistics. In fact, he looked at also Minkowski functional and wavelet-based analysis in future forecast. However, the price we pay for this is that there's no analytical predictions for it. So we need to use simulations to perform the prediction for a theoretical model. And then we need to scan the parameter model. So we need to make many, many simulations. And he did that by using an array of simulations spanning a wide range of parameter space. And then he used an emulator technique to interpolate between the simulations. And the simulation is what we call forward model simulations. So they involve simulating, including a lot of the physics that goes from the sky to the observation. So it includes adding noise, adding some systematic effects, adding the masks and so on. And what you see here is one of these simulations using the same mask as the DES Y3. And you see that at least qualitatively, they agree quite well. This is, of course, for one of the cosmological model. And there's a range of tests that are done, a wide range of tests to test that the simulations are in agreement with the data. And this simulation includes various systematic, like intrinsic alignment, tests on baryon physics, amplitude, calibration of the shear signal, and others. So that's the measurement. And what you see in the colored curves are the predictions using this simulation for these peak counts for different values of sigma 8. So in blue, it's low sigma 8, and in red is large value of sigma 8, just to illustrate the sensitivity of the peaks on SH. It's not surprising because the higher the amplitude of the matter power spectrum in the model, the more peaks we expect because more nonlinear structure will form. Once we have this, the emulator, based on the simulations we can do, and the data, we can do a Bayesian analysis and get cosmological constraint. So this is what we found. So here you see, for example, let's focus again on this S8 omega m constraint. So what you see in blue is the constraints from the CLs, so the 2-point function. In orange, the constraint from the peaks, and in green, the combination of the two. So you see that the peaks provide information beyond the 2-point function. It's complementary, and in fact, can reduce the size of the contour. What it does actually is it gives a lot of information on nuisance parameter, which is the amplitude of this intrinsic alignment signal. And if we look at the projected plane between S8 and this amplitude of the intrinsic alignment signal, basically you can think of one systematics, you can see that the CLs and the peaks give sort of different, well, complementary constraints, and together they give much tighter constraint on this intrinsic alignment. This is what helps in getting better constraint on the cosmological parameters. And then we can compare, for example, with Planck. So here is these are the peak constraints plus CL. This in pink is Planck, and in orange red is the kids measurement using the 2-point function with this other survey called kids. And again, we see somewhat of attention, but less so than with kids. We can also compare with the DES 2-point official analysis in pink compared to this peak analysis in green. They're consistent, slightly higher, but consistent. So again, this would be the official DES 2-point function, and this is our peak plus CL analysis. So very nice check, very different approach, giving constant results. All of these were blinded analyses, and it's very good, very reassuring that we see consistent results and smaller constraints. Okay. Another approach is to go one step further. So already by going to map level statistics like peaks, we gave up on analytical predictions, okay, in order to potentially extract more information, more non-Gaussian information. And we can go already one step further, and this time is using machine learning. So the idea is the following. So to illustrate what we were doing before, we have a data weak lensing map, which is a data. We compress information using a summary statistic with the peaks of the 2-point function. We compare that to a prediction, so either analytical or from numerical simulations. And then we do a Bayesian analysis and get cosmological constraints. So that's the two other approaches I was telling you before. The idea now is to go directly from the measured mass map to the cosmological constraints using machine learning. And the way we do it is by training a convolutional neural network using a very wide array of numerical simulations in which we tell the machine, this is a mass map corresponding to these parameters. This is a mass map corresponding to another value of the parameters. And we give the machine a very large number of such pairs of data and answer, basically. And then we give the real data to the machine and ask it, what is the model corresponding to the data. And we can do it with also a Bayesian analysis and get constraint on the cosmological parameters. So this has the potential of measuring even more non-Gaussian information. Machine learning is very good at detecting very weak correlation in data. Basically all the physics is contained in these simulations, but we no longer go through a summary statistic designed by humans, and even less going through a theory code that computes the prediction for the summary statistic. So we did this at first. This is by another student, Yanis Fleury at ETH. First, in a simplified setting using the kids for 50. So this is a public data with 450 square degrees of the kids survey. What you see here, it was varying very few parameters and mainly sigma 8 omega m, including all various systematics as well. And you see the constraint from the power spectrum in green and in blue for the using the machine learning. And you see that the machine learning has smaller constraint from the power spectrum, and therefore it was capable of not only extracting information at the level power spectrum, but even beyond the power spectrum. So it's quite impressive and promising already at the time, showing that the machine can can extract non-Gaussian information. You can see the comparison with Planck. So in blue is our results using the machine learning. In green is Planck. And then you can see the official kids. We're not part of the kids collaboration. So this is coming to public data. The kids' 2-point correlation function in red here. And we find result a little bit higher than the official one, but consistent. So a little bit less tension with Planck. Because of technical constraint, we couldn't use as many scales. We couldn't go to as small scales as they did. So our constraints are a little bit, our 2-point function constraints are a bit larger than them. But that was very promising in these sort of somewhat simplified analysis. Then Yanis did an analysis, which was the first full analysis of a weak lensing survey with all the systematics, all the cosmological parameters, just like we would do for a 2-point function analysis. This is done with the kids 1000, so the next data release of the kids survey. And this is a WCDM, so lambda CDM plus the W parameter. And you see the contour here on the sigma 8 omega m plane. So in black is the power spectrum, in blue is the convolutional neural network, and in green is the official kids analysis. By the way, all of these are also blinded, even the ones from before. So even the machine learning analysis is blinded as well. Okay, so this was blinded. So we see that we get results which are a little bit better than the 2-point function and consistent with the official analysis. You see the result on sigma 8 for our machine learning analysis for the 2-point function and the kids official analysis here. You'll notice that our results are, this is with baryonic correction and without taking into account baryonic correction. You'll notice our results are still a little bit broader than the official kids analysis. And that's because, again, for technical reasons, we couldn't go to very, very small scales. Also, on very small scale, one has to be more careful with systematics. So as a result, we're a little bit conservative in our analysis, but we find in this blind analysis something consistent and with a small improvement over the 2-point function. So that's quite impressive. And it shows that the machine learning now is almost on the same footing as the other map-based or 2-point function analysis. The only step we need to do is scale it up further to be able to go to smaller pixels, higher resolution. Yep. Yeah. Yes. Yes. The gray. It's hard to see, but the gray band, which is the size of this fiducial result for the machine learning, is a little bit increased because we have an additional parameter which characterizes the amplitude of the baryonic corrections. So we're quite conservative in choosing the scale. So we use only scales that are not too affected by baryons, but there's still a little bit of an effect. So when we include it, the errors go a little bit larger, which is typical of what we see also in other analysis. The more, if we go to even smaller scales, the ratio of the error bars from without the baryonic correction and with would be even larger. How much time do I have?
Probably about 5 minutes.
Okay, good. All right. So this yeah. So this was quite promising, and then so of course we're planning to do more. In fact, we're working now on a DES Y3 analysis to do this measurement with even higher precision. It's ongoing right now. In the future, there will be further surveys. Partially, there'll be stage 4 surveys. This is a forecast analysis done by Dominic Zürcher and different people in our group as well, in partly Virginia Ajani. And then what you see is the prospect. So this is a study not only does forecast, but prepares the way for doing analysis with even more data, which requires scaling up this simulation effort even further. What you see, for example, if you look at the S8 omega m plane, you see the expected constraint with the 2-point function for a stage 4 survey like LSSC or Euclid. And then what happens if we add the peaks and other non-Gaussian statistics, we expect to get much improvement on these parameters and also on the intrinsic alignment as well. Now, in order to do this, we needed to run very large simulation suite. This last analysis I showed you on the DES, on the KIDS 1000, Machine learning was done with this Cosmo grid, which is one of the largest suite of simulations that was run and that we use to forward model the weak lensing maps and do this analysis. It spanned a very wide range of model parameters. You see each of these dots. This is a different cosmological parameters. Each of the dots is one simulation. Each simulation has several realizations. We use 2,500 unique cosmologies, various realizations. We also have one fiducial cosmology with even more to compute covariance matrices and so on. We have different cosmological probes that are that we can forward model. This is public. This is from a paper by here, Kaprak and Fleury et al. You can see the simulations are available here if you're interested and want to use it for various purposes. The map making was done with a code that we call UFalcon, which is a fast light cone generator that generates maps. This is an example of one of the weak lensing maps that we generate. We compare the weak lensing map statistics with theoretical prediction when they exist. And we've implemented the weak lensing, but also CMB lensing, the ISW, and galaxy clustering as well. And you can find the code here, at least some version of the code. We are in the process of updating it with more probes. So what we will get, basically, what we can get is maps for the different probes for a wide range of parameters for anybody who wants to do a map level inference. If you're interested, we also have developed a theoretical tool for theoretical predictions as well. This is called PyCosmo. This is a Boltzmann, Einstein-Boltzmann solver. This characteristic is that we use symbolic representation of the Einstein-Boltzmann equations. And then what we do is we have an automatic code generation that goes from the symbolic equation directly to fast C++ code using a package which we call a SymPy2C. The idea is to try to speed up the implementation of new theoretical models, right? So if you have a new theory of, I don't know, interacting dark matter or anything, the idea is that one can add equation to the equation system and then the code gets generated without having to code yourself, at least in principle. In practice, of course, it's never that simple. But the idea is that we can explore faster a large set of extension of the lambda CDM model. And we compute observables as well. The code is available if you want. And also there's a Python notebook hub where you can directly log in and directly have access to the code without installing it on your machine. So it's kind of a cloud version of it if you're interested. And feel free to come and see me if you want to know more about these different tools. So together, this suite of codes allows us to do this full analysis, both with analytical results, analytical method, map-based, and eventually machine learning as well. So to conclude, weak lensing has an important role in cosmology. It highlights this tension, this relatively 1 to 2 sigma tension in sigma 8. And these three approaches, which are complementary, will continue in the next generation of surveys. And in particular, the map level and machine learning have a great potential to obtain smaller and smaller cosmological errors. Thank you.
Questions?
Hi. So firstly, for the PyCosmo thing, how did you fix the nonlinear? Can you explain a little bit more about how you included nonlinear perturbation?
So nonlinear, we do it in the usual way. So we have different recipes to compute nonlinear corrections. So there's the, the halo-based like Mead et al. Model. There's HaloFit. We've now are in the process of plugging different emulators that have been developed based on n-body simulations. We also have other techniques like KFT and others that we're in the process of implementing. One of the idea of PyCosmo is that it bridges the gap between the theory and the observables. So we put a lot of the observable, the systematic effects, predictions, and so on. The other aspect is that we try to have, as much as possible, all the different recipes available in the same code, so that to do code comparison is very convenient, because then we can choose the recipe chose by the other codes, other analysis, and compare with ours. So that's one of the multiple aspects, but it's still under development, so we don't have everything in yet.
One more question. why did you exactly choose the CNN model? Is there any specific advantage that that machine learning model has for your?
So we worked a lot with CNNs before. We work in collaboration with the computer science, machine learning experts. I mean, the CNNs are quite natural to deal with images. So that's kind of the first thing to try. And they worked quite well out of the box. It's quite interesting. We tried different architectures. And it's as long as it has, well, roughly speaking, as long as it has enough complexity, the results are quite robust to changes in the CNN architecture. We're also looking at others as well now, but the CNN worked. And as I said, it's a kind of natural choice.
Okay.
Hi. So I had a question regarding the distortion matrix.
Mm-hmm.
So what it seems to me is that at any given time, there's always one remaining degree of freedom in the problem, in the sense that we do not know the properties of either the lensing object or the object being lensed. So there's only a constraint between them. You mentioned in a previous question that you look at the correlations between images and try to find things out. So what if in a line of sight, there are more than one source? So how would you differentiate between images between two sources and
More in one source or more in one lens?
more than one source? So
So yeah, that's a good question. So I mean, basically, you can think of it if we look at the 2-point function real space, we take pairs of galaxies and we look at the correlation in their shapes. Now, the two pairs that we pick could be at completely different redshifts, right? So one could be a very high redshift, one could be a low redshift. Now, the lensing effect, right, is, I mean, they would still be lensed by the structures between us and the galaxies which are more nearby. Even the more distant one is lensed by these same structures. So it means that there will still be a shape correlation between the two, generated by the structures that are in common, that has lensed them both, okay? So that's a very specific nature of lensing, is that it produces correlation even if the galaxies are far apart, physically far apart. On the other hand, effects like intrinsic alignments, at least some of them, are only relevant if the galaxies are close together, so that they are actually physically, there's a physical correlation, so they need to be close together in redshift. And so what we expect is that the intrinsic alignment is strong, at least the main component I'm talking about, to be stronger when the galaxies are close together, while the lensing one is much less dependent on the physical separation between the two. That's how we disentangle the intrinsic alignment from the lensing effect, through the signature in redshift, in the redshift dependence.
Thank you.
Hi, first of all, thank you for the nice talk. So my question is, okay, your model is fine for the case when we have only one lens between the source and the observer. What about the case of multiple lensing?
The multiple lenses, they are. So yeah. I mean, here, I show it here, there are many, there's various structures between here and here. There's different structures, it's different clusters, filaments, cosmic web. So there's an entire, I mean, this, typically the galaxies are redshift 1, this is redshift 0, so there's a lot of structures. And so the lensing is produced by multiplane. It's a multiplane lensing effect for all the structures along the line of sight. In the simulation, that's taken into account in the analytical predictions as well.
So you are saying that like the method which is being adopted, so we can decouple different sources which are causing lensing.
So if you have galaxies only at one redshift, then all you get is a projected map, a projected mass map. You have what you map is the projection of all the structures along the line of sight, projected, weighted by the lensing kernel, which peaks halfway in between, roughly speaking. So you cannot disentangle. But if you have galaxies at different redshifts, which we have with these different redshift bins, then we can do what we call a tomographic analysis and get some three-dimensional information. The redshift, the radial information is have a very, very low resolution because the lensing efficiency function is very broad, but nevertheless, we can get back some three-dimensional information. Some people have tried, I mean, we did it too, to make even a three-dimensional mass map of the structures. So it's quite noisy, and not very high resolution, but one can. That's called weak lensing tomography.
Okay, thank you.
Okay, so we've got the last question here.
You had shown a plot of constraints on the asset omega and plane with CLs, peaks, and then CLs combined with peaks.
Yeah, let me try to. Yeah. This.
Yes.
Mhm.
You said that the peaks measure the tail of the probability distribution. So
Sorry, the peaks?
mention the measure the tail of the density
The,
distribution.
yes.
That also includes a 2-point function, right? So what information do the CLs have that the peaks don't have?
Yeah, so the peaks, well, as the name indicates, measure the peaks, which is the tail of the distribution, the higher end of the distribution. While the 2-point function is more sensitive on the sort of the bulk of the distribution, right? The width. I mean, the 2-point function is actually the width of the distribution, and the peaks tells you about the tail of the distribution. And due to nonlinear clustering, which I try to illustrate here, what happens at early times, the field is thought to be Gaussian and symmetric around the mean. And then as time goes on, it develops a tail from nonlinear instability. And that's what the peaks allow you to probe, which is complementary to measuring the width. That's what we're doing, really. And the 3-point function, 4-point function, and there's also various other statistics that are being developed by Arka and collaborators, Tom and others, which does this in different ways to probe different aspects of the distribution and also the correlation in space as well. That's what we're doing. And it's an open, very interesting problem is how you fully characterize a non-Gaussian field statistically. That's still an unsolved problem. We have various statistics. We think that we can characterize most of it. As far as I know, there hasn't been a proof of, I think we discussed it when we were in Stanford, right? That a proof of what's the maximum information content of a non-Gaussian statistical map like this, right? So what we can do is add more and more statistics or use machine learning and hope that we get closer and closer to the maximum information, but we don't know whether there could be even more that we can extract. So that's an interesting problem if you want to think more theoretical, is how you fully characterize these non-Gaussian statistical random maps.
Just one plot.
Yeah.
So in that plot, why are the constraints from peaks stronger than those from the CLs? Can you explain why the peaks are more constrained?
I mean, I don't know if they're more constraining. I mean, if you look at, I mean, for example, in omega matter and omega matter sigma 8 here, you know, they're a little bit, yeah, maybe here in this case, they're a little bit more constraining. I don't really have an answer. I mean, I think in here, it's a little bit complicated. Also, you have to be a little bit careful because it depends also on exactly what scale you use and what scales are weighted. I mean, here we try to match the scale of the scales of the peaks, but it's not an exact match, so one needs to be a little bit careful. I think one thing where the peaks are quite powerful is its intrinsic alignment, because of course that depends on the model that we use. But the peaks basically probe the very high density region, which have a sort of different, well, the intrinsic alignment have a different response for high density and low density, and that can break that degeneracy. So it's, and you can see it here. So I think it comes from that aspect.
Okay, so we best move on to the next speaker. So let's thank Alexandre again.